it generates, so we unite it with A. And you can see that we can write this as S union singleton 1 by what seems to be factoring A on the right, by the right. And looking at S union singleton 1, we will see that it is nothing but S1. We have learned about who is S1 in our previous lectures. This is called the principal left ideal generated by A. Now, an equivalence L on S is defined by the rule that given two elements in a semigroup S, A and B are L related if and only if they generate the same principal left ideal. Meaning that if and only if S1A is the same as S1B. Similarly, the relation R is dually defined in a similar manner. That is, two elements A and B in S are R related if they generate the same principal right ideal generated by A and B. If they generate the same principal right ideal, we simply say A and B are R related. So in a summary, we can just have these definitions that let S be a semigroup and S1 be a semigroup. Now, for A, B in S, A and B are L related if they generate the same principal left ideal. And they are related if and only if they generate the same principal right ideal. These definitions, given any semigroup, one can use this definition to characterize this relation, especially if the semigroup have few number of elements, like if S has some few number of elements. But one thing you need to note is that if S is an arbitrary semigroup and it has infinitely many elements, computing this set will not be trivial. To compute S1A will not be easy, and similarly to compute S1B will not be easy. And note that one have to compute all these sets for all the elements in S. So sometimes using definitions used to be tedious or difficult, and at times one have to use algorithm or programming in order to make this type of computation. So, however, one can show as an easy exercise that actually these relations are equivalences on S. So the following proposition is a direct consequence of the above definition. That is, let A, B be elements of a semigroup S. Then A and B are L related if and only if there exists X, Y in S1 such that XA equals to B and YB equals to A. So instead of using the previous definition, one can actually use this proposition, because you can see here we are using arbitrary elements. If you can have XY in S1 such that this happens for any A and B in S, whenever this happens, we can claim that the other definition holds. So we can demonstrate similarly for the R, that is A and B are related if and only if there exists UV in S1 such that AU is equal to B and BV is equal to A. We can demonstrate one of these proposition to see how we can deduce such. For example, if A and B are L related by the above definition, it means that S1A is equals to S1B. And from here, that is to say, because S1A is nothing but S1 union singleton A, and S1B is SB union singleton B. And from here, one need to note that A is in this set because it is here, So A is in this set. So if it is in this set and this set is equal to this set, one can claim that A is automatically in this set. And of course, this set is S union singleton 1B, or you can just call it, instead of S union singleton 1, we can just call it S1. So we are just saying A is in S1B. Now, if A is in this set, it means that A must look like an element of this set. And elements of this set will look like X, some small x, B. And in that case, A will look like XB for some B in S1. So in a similar fashion, one can demonstrate that B is equal to YA for some Y in S also. Now, the next property of L and R is as follows. We have, in one of the previous lectures, we have discussed about the congruences. Now here, L is a right congruence, and we are saying R is a left congruence. By a congruence, we can recall that a congruence is an equivalence relation which is both left and right congruence. But L is not both left and right, but we are sure it is a right congruence. And R is not both left and right, but we are sure it's a left congruence. We can demonstrate one, that is, to show that L is a right congruence, we need to notice that L is an equivalence on S. It's an equivalence relation on S. As such, it is enough to show that L is right compatible. Because if you could recall from the definition of a congruence is an equivalence relation which is both left and right compatible. But here, L is only right. So if it is only right, it will only be right congruence. So how do we go about that? We can assume A and B are L related and pick a C in S. That is, S1A is equals to S1B using the definition, and C is in S. We are free to multiply C on the right of the previous equation. So we have here, C here from the previous equation. So meaning that, and by definition, this means what? AC is what? L related to BC as required. Now, intersection of two equivalences is also an equivalence. So the letter H is reserved for the intersection this. And also the join of two equivalences. We have seen in the previous lectures how the join of two relations is defined. And this join is of great importance. It is denoted by D. It is also an equivalence. So we might have seen in section 1.5, to be precise, this proposition that to determine the join of two equivalences is not trivial. You need a chain for some natural numbers. Before A and B are linked, you need a chain. So it is really not trivial, but in this case, in the case of L and R, the join of L and R, this difficulty has been saved from the following proposition. And the proposition is proposition 2.1.3 that the relations L and R commit, i.e., L composition R is the same thing as R composition L. Once we achieve this, then we also have an end result that will simplify these relations further. So let us demonstrate how to prove that these two relations are equal. Of course, L composition R, one thing you need to take note is a set. It's a set of pairs. This is also another set. And we're saying two sets are equal. And to prove that two sets are equal, all you need to do is to prove that L composition R as a set is a subset of R composition L, and R composition L as a set is a subset of L composition R. So
Now let S be a semigroup and let A comma B be in S, and we now try to pick an element in R composition L. Of course, the other way around has been shown in the text, but let's show this wrong. So now if we pick A comma B in this, by definition of composition, it means you can find some C in S such that A is R related to C and C is L related to B. That's the meaning by the definition of composition. So, and we know from that proposition that if A is R related to C, it means you can find some x comma y in S1 such that this equation holds. And if C is L related to B, it means you can find some u comma v in S1 such that this equation actually holds. So now we can denote the element ucy of S. Of course, this element is in S because UC, we can see UC is B, but already also Y is in S. So if you multiply U, C and times Y, it will also be another element of S. So if we denote this UCY of S by D, then one can see that UE from where? From here. From here, can you see it from here? Meaning that multiply this equation by U, you have UCY is equal to UA. So it means UA is equal to UCY, which is what we denote as D. So we got this. Next, VD. VD commit, this is equal to this. So we can use this corollary now on the Green's relations L and R, and this follows from that corollary. We know D is defined to be the joint of L and R. So it is now, and since this commutes, so it means this is equal to this, and this is equal to this. So in fact, D is the smallest equivalence relation that contains both L and R, meaning that L is a subset of D, and R is also a subset of D. Yes, we can demonstrate some of this result as a lemma. This you cannot find this in the text, but you can find it in lecture note on semigroup theory by Terhaji. That D is the smallest equivalence relation that contains both L and R. So let us demonstrate one. Firstly, we need to show that L is a subset of D and R is a subset of D. But now, if A and B in S are such that A comma B is in L, what does that mean? Notice that R is reflexive. I think here it should be L. Oh yeah, R is reflexive. I.e., what does that mean? It means
for any x in S, x comma x is in R. That's the meaning of R being reflexive.
So in particular, you know, A comma B, we pick the two elements from S. So automatically we have picked B from where? From S. So, and if this condition holds for all x in S, then in particular, B comma B will also be in R. That is, in particular, B comma B will also be in R. So now you have A comma B is in L, and at the same time you have B comma B is in R. By the definition of composition, what does that mean? It means what? A comma B is in L composition R. Who is L composition R is D. So you can see that we pick A comma B from L, and now we have shown it is here in D, i.e. A comma B is in D, and hence L is a subset of D. One can use this argument to show that of R is also a subset of D. So here, so now, so in order to show that D is the smallest equivalence relation containing, because we say it contains L and it contains R, we can just summarize it as saying it contains L union R. Yeah, because L is in D, R is in D, so union is actually in D. So in order to show that D is the smallest equivalence containing the union L union R, we can assume an equivalence, say C, containing L union R, and we try to show that D must be sitting inside that C, meaning that given any equivalence relation which is containing L union R, D is in that relation, and D, by so, it means D is the smallest. So now, we can now let X comma Y to be in D. So the goal is to show that X comma Y must be in this C. And once that happens, then D is always here. So what does that mean? By definition, it means you can always have a C in S such that A and C, A comma C is in L, and C comma B is in R. And this means what? If A comma C is in L and C comma B is in R, it means A comma C, C comma B is in the union, L union R. If you unite the two, L union R, A comma C, C comma B, these two elements will be in the union. But we have seen that the union is in C. So what does that mean? A comma C, C comma B are elements of C. So by this, what do we know about C? We should recall that we assume C to be an equivalence which contains this. So since C is an equivalence, we already have A comma C comma B in C. We need to remember that C is transitive. So whenever you have A comma C comma B in C, C being an equivalence relation, it is transitive, then it means A comma B will be in C. So that is, recall that C is an equivalence relation, i.e. it is transitive. So this A comma C, C comma B in C implies A comma B is in C. Where did we pick A comma B from? We picked, oh, did I use A comma B here? I should have used, so here is a typo, it's supposed to be A comma B. I use X comma Y. So here is actually a typo, it's A comma B. So the A comma B here is in D, and it implies A comma B is in C. So as such, D is a subset of C as required. So now our final equivalence to discuss is the two-sided ideal analog of L and R. That is the principal two-sided ideal of S generated by A, which is S1A, S1. And the equivalence G is defined on S with respect to the definition of the two-sided. That is the rule that two elements are J related, A and B, if and only if they generate the same principal ideal. That is S1A S1 is equal to S1B S1. And that is to say, if and only if there exist four elements in S1 such that XAY equals to B and UBV equals to A. I think it's an easy exercise to demonstrate this. From this definition, one can actually get this, similar to what we have done in the previous proposition. So it is clear that L is in J and R is in J by the previous definition. We can demonstrate one, that if you let A comma B to be in L, automatically you have this. And if you have this, you can multiply on the right of this equation by S1, S1. So you have S1A, S1 is equals to S1B, S1 using the definition. And automatically one have A comma B is in J. So you see really L is a subset of J, and you can show in a similar way that R is a subset of J. And of course, if that is the case, even the union is in J. Now, but since D is the smallest equivalence, here you can see L, since L is in J, R is in J, the union will automatically be in J. But don't forget, even D contains L union R. The union L union R is in D. And here we have also seen that L union R is in J. But what we have seen earlier is that D is the smallest equivalence containing L and R. So since J is another relation containing L union R and D is the smallest, then D must be in J, meaning that D is a subset of J. We must have this. Obviously, we must have this. So now this inclusion can be strict. Sometimes it's strictly contained in J, as shown by Green in 1951. And another example is by Anderson in 1952. You can look at the text on page 60, exercise 2.6, number 1, where a simple and translative subgroup was used to prove the claim. So you can go and try that and see. In that particular example, D is strictly contained in G, meaning that you can still have some element in G which are not in D. So, and that has been shown. In certain classes of semigroup, we do have equality. That is, in some semigroups, D and G are equal. D and G are the same. We shall see this in the next few slides. And in a commutative semigroup, if a semigroup S is commutative, I'm sure you have discussed about a commutative semigroup. These relations, the H, L, R, and D and G coincide, they are equal. They are equal. And similarly, in a group G, we have just this to just be the universal relation on G. That is, it's just J cross G. That is, they are all equal and they will be G cross G. You can demonstrate these two. Less trivially, we have a result which implies in particular that D equal to G in every finite semigroup. But before then, let us recall the following proposition. we have discussed, this proposition has been discussed in some of our previous lectures. That is, in a periodic semigroup, every element has a power which is an idempotent. Hence, in every periodic semigroup, in particular, in every finite semigroup, there is at least one idempotent. So if you have a periodic semigroup, a finite semigroup, you usually have an idempotent. I.e., what does that mean? That is, for all A in S, there exists a non-negative integer, say n, such that A to power n square is an. That's the meaning. That is, A to power n is an idempotent. Here we can write it as A to power n is element of E of S. E of S, we must have seen this notation in our previous lectures. E of S denotes the collection of all idempotents in S. So it means that in a periodic semigroup or in a finite semigroup, this property holds. So we now have the following proposition. That is, if S is periodic, or if S is finite, then D equal to G. That is, these relations are equal. So in a finite semigroup, the two relations are the same. Now, to prove this, it suffices to show that J is a subset of D. I'm sure we have seen in our previous two slides that D is a subset of J. So here we need to show that J is sitting inside D. And to do that is to pick an element in J and show that that particular element is in D. How do we do that? Now we suppose A comma B is in S as such that A comma B is in J. Then it means that you can have X, Y, U, V in S1 such that X, A, Y is B and U, B, V is A. So to prove the desired result, we need to find an element C in S such that A, L, C and C are B. This is what we need to do. Because we pick A, B in G, so we need a C that will link A and B by this composition. And once this happens, we know L composition R is D, and then automatically A comma B will be in D. So now, from this equation 1, we can have some sequence of equation from equation 1. Notice that A here is UBV. But the B in the middle from the same equation is XAY. So we can insert it like this, and we have U is equal to XAYV. Then a semigroup S is associative. We can associate UX. We leave A at the middle, YVA at the middle, and A again. We can reinsert it again. A is UBV. So you can see we insert A here, UBV. And again, we can associate to have UXU, B at the middle, VYV. But B is again XAY. So we can replace B with XAY. So you have UXU, XAY, UYV. Now we can reassociate again and allow A to be at the middle. So you can see what we have now is now building, is becoming bigger. So we have UX, A, YV, YV. But UX can be written as UX squared. By square here, it means UX operation UX. So, and similarly, by square here, it means YV operation YV. So here, one have A to be equal to UX all square, A, YV all square. And of course, it's UX, A, YV. So if you continue in this fashion, you realize that A is equal to UX, A, YV. It's as if this is to power 1, the next one is to power 2, the next one is to power 3, and it's going to continue in this fashion. And similarly, B will behave in that manner. If you pick B, you can also have B to the XU, B, VY, which is equal to XU square B, VY all square, which is equal to XU to power 3, continues like that. So now, but what do we know about S? Who is S? S is periodic. So if S is a periodic semigroup, we know each element has if you raise it to power some integer, it will become an idempotent for any element of the semigroup. So in that case, we can, by that proposition, we can find a non-negative integer m for which this ux, which continues, will terminate, or it will become an idempotent. That is, ux to power m is an idempotent. So then if we let c to be xa, we find that a is equal to ux power m a yv to power m. This is where it terminates. It becomes an idempotent, and once it becomes an idempotent, the product keeps repeating. So here we can write this product. Notice that this product can be written as ux m ux to power m. Why? Because ux is an idempotent. Ux to power m is an idempotent. If you multiply it by itself, it does not change anything. So instead of ux to power m, we can write it as ux to power m operation ux to power m. And here you have your a yv to power m. And similarly, you can associate a and this from this particular ux to power m to yv to power m can be associated in this manner, so that the whole of this is who is a. You can see the whole of this is a, ux to power m a yv to power m. The whole of this is a. So we can just have this. And at the same time, this is the same as ux to power m minus 1 operation ux. We'll still go back to ux to power m, so that we can associate this uxa, and so that we can associate xa. So the product xa, we let it to be c. So we have ux to power m minus 1 u operation c. So by this, one thing you need to note is what we have just shown. We have shown that a is L related to the c, because here we see c is equal to xa, and a is equal to some element, because this element uxm minus 1 u is some element operation c. So what we have shown is actually a is L related to c by definition. Also, cy is xay, and xay we have seen from the previous slide is b. And if we choose n so that vy to power n is an idempotent, we see that c is equal to xa, and this is equal to who is a. You can write this as ux to power n plus 1 operation a by n plus 1. So we can, instead of, we can split this. Instead of here we have x operation this a yv to power n plus 1, we can write this as xu to power n plus 1 x ay, then yv to power n, then what, v. And of course this v is outside, and this vy is an idempotent. This vy is an idempotent. So since it's an idempotent, you can write it as vy to power n square, and that will just give you vy to power 2n, and that's exactly what we have here. But xay is b, xay is b, and here you have vy to power n. So you have, which is an idempotent, which is vy to power 2n, then multiplying this v, and this can be written as now vy to power 2n. You can write it like this, because vy to power n plus 1 times vy to power n minus 2 is still vy to power 2n, because 1 minus 1 will go, n plus n will give you 2n. So in that case, what are we having? So we just splitted this vy to power 2n in this format. So if you look at this, this is b, xu to power n plus 1b, vy to power n plus 1 is actually b, and you have multiplying vy to power n minus 1 times v. So what we have c is equal to b times some number, some elements, and that means C and B are related, because here CY is equal to B, and C is equal to B times some elements. So thus all what we have is C is R related to B. So therefore, the two, using the two, A is L related to C, and C is R related to B, means A comma B is in D, and as such, J is a subset of D, and that's exactly what we have proved as required. And from the two, we can see that the two coincide. We will also discuss another class of semigroup in which J equal to D. But first, let us have some preliminaries, some notations that for the L class, and respectively R, D, H, and J containing an element A is usually denoted by LA. But once we write this LA, it means this is an L class containing A. Any element in this class is related to A. That's the meaning. Any element in SL class is related to A by the relation L. And respectively, the others follow suit like this. Now, recall that L, R, and G are defined in terms of ideals. Thus, the inclusion order among these ideals induces a partial order among these equivalence classes. And this partial order are defined as in equation 2. That is, if S1A is a subset of S1B, then automatically you see L1 is less than or equals to LB. So we define it this way. That is, L1 is less than or equals to LB if and only if S1A is a subset of S1B. And of course, if at the same time S1B is a subset of S1A, you know, here one will have LB is less than or equals to LA. If you have the two, you have LA is equals to LB. And if you have LA is equals to LB, it means A and B are L related. And you see, if A and B are L related, you have equality here. If S1A is a subset of S1B, automatically S1B will be a subset of S1A. So, so this is one way. So this partial order is like one way of the definition of the equivalence we define of L, the Green's equivalence, L, R, and the rest. So these relations, these are partial orders among the equivalence classes. So R is defined in this way, and J is also defined in this way. Thus, S by L, that is this sets, is partially ordered. That is S by L with respect to this, S by R with respect to this set. We can look at it as like a quotient set, but it's because here L is not a congruence, you don't look at this as a semigroup. It's not necessarily a semigroup. They are just quotient sets induced by these orders. So these are all partially ordered sets. So notice that for all A in S and for all XY in S1, we have this. S1X is always a subset of S1. And if this is true, then we can multiply on the right by A to have S1XA is a subset of S1A. And if this happens, then this is always true. LXA is less or equals to LA. That does follow from here. So it's just from this simple argument. That's for all A in S, XY in S1. S1X is a subset of S1, that's true. Multiply on the right by A, you have S1XA is a subset of S1A. So, and by this, using equation, the definition we just had in the previous slide, we can just conclude that LXA is less or equals to LA. Similarly, others follow suits for R and G. So notice also that one can demonstrate that if LA is less or equals to LB and JA is less or equals to JB, if LA is less or equals to LB, it implies JA is less or equals to JB. Yeah, one can actually demonstrate this, and one can see it from the definition above. And similarly, if RA is less than RB, JA will also be less than JB. So now, if the partially ordered set this satisfies the minimal conditions which we have discussed in section 1.3 in our previous lectures, then we say that the semigroup S satisfies the condition min L, min R, and min J respectively. Once these orders satisfy the minimal conditions discussed in that section. So we once they satisfy the minimality condition, this set satisfy those minimality conditions, then we say that the semigroup S satisfy min L, min R, and min J. So one can just go and check. Now, the next class of semigroup that J and D are the same is those that satisfy this main condition. That if S is a semigroup satisfying mean L and mean R, then J and D are equal. Now let's see how to go about the proof. Suppose that S satisfies mean L and mean R, then so does S1, since S1 has exactly the same principal length ideal and right ideal as X, except in the case where S1 is not S for S1 itself. So one can assume that S has identity element. So it is just enough to show that J is a subset of D as usual, because all the time D is in J. D is a subset of, so all the time once you show this, then the equality holds. Now, so we pick an element A comma B in J, and as usual by definition, you can find PQRS in S such that PAQ is equal to B and RBS is equal to A.
Now, if this is true, then this set, the way Amanda, look at the way Amanda will define the set, X in S such that there exists Y in S, XAY equals to B. This, the way Amanda will define this set surely will not be empty, and that is true from here because A and B is in J. Surely we can, this equation holds. At least there is a P. P is in X. One can easily see that this P is in S because P satisfies the conditions PAQ equals to B. So you can see P is an element of this capital X. So at least this set is not empty. And if it is not empty, so also the subsets of S by L, that is this subset lambda, that is the LX, such that X is in L, is also not empty. So the condition min L allows us to select a minimal element inside this set, and we can choose, once we select the minimal element here, we can choose an element V in S, such that, and you see the element we pick in lambda is LU, so we can always be done. Now, look at this product, URU is multiply AVSU. We can associate UAV in this form, UAV in this form. So you have URUAVSV, but UAV is B. So you see you have URBSV. And you can at the same time associate RBS. So you have U multiplying RBSV, and RBS is who? RBS is A. We have seen it. RBS is A from the previous slide. RBS, you can see it here. RBS is A. So here we have this is A, and you have UAV, and UAV is your B. So what are we saying? All we are saying is URUA, USV is B. And if this is true, then this URU, LURU must be an element here. LURU must be an element here because we can write this. So LURU is in this set. And if LURU is in this set, then from equation 3 in the previous slide 17, we have LURU is less or equals to what? LU. And by the minimality of LU in this, because we are saying this is minimal,
So if it is minimal, it is less than every element in the set. So it follows that they are equal. This and this are equal. LU is equal to LURU because LURU, LURU is less than or equal to LU, and by the minimality, LU is less than LURU. So it means they are equal. So they are equal, but this
Hello? Walaikum salam. Champion biyu children. Children. Eh. Ka samu A12 din nan ko? Akwai wata A12 wanda nema magana nan ta WhatsApp ɗin ka gane su. Da sai kofukan nan. Yawa sai kofukan nan. To bari in duba. Nawa ne kuɗin?
UAV is B. And so you just have RB is L related to B. So using the condition in R, and together with the fact that R is a left congruence, so we can also follow a similar procedure, and one can establish that BSRB and RBS RB, i.e. A and RB are related. So you can use the same argument here. We demonstrate to also show that A and RB are related. And here RB and B are unrelated. What does that mean? You have A is R related to RB and RB is L related to B. Then by the definition of composition, this is telling you that A comma B is in D as required. So we pick A comma B from J, and now it is in D, so it means J is a subset of D, and now the result actually follows. So we have shown about two classes of semigroups in which these two relations are equal. That is, if S is a finite or a periodic semigroup, the two relations coincide, J and D are the same. That's why you find out that many researchers are studying this relation on transformation semigroups, finite transformation semigroups. They don't care about the J because D and J are the same. So now we have the following remark. It is now clear that the following inclusions are true. L is a subset of D. We have seen that. You've seen that. L union R is a subset of D. H is in L because H is the intersection of R and L. So it is in L and it is in R.
Yawa na gani nawa yake shi? Nawa yake, yana sauki dai ko? Sai kana ji? Kana ji na? Sai wani jog din nan na sama hoton shi a WhatsApp. Wani mai kula na haka. Na sama hoton, ka duba WhatsApp ɗinka. Shi ma har da shi. In akwai kala biyun ma duka kala biyun.
Yeah, some few observations are as follows. If a semigroup S is L trivial, meaning that the relation L is just an equality relation. Two elements are L related, C, A, and B, if they are equal. So if S is L trivial, then the relation L will surely be a congruence. You can sit down and verify this. Is R trivial, the relation R is a congruence on S. So also the rest of the relations we can verify. Another S to be a commutative semigroup. Of course, if S is a commutative semigroup, the two relations L and R will surely be a congruence. You can also verify this. And of course, we have seen that in a commutative semigroups, L is R, is D, is equal to J, they are all the same. So a stronger sufficient condition is S to be a group. This you can as well verify. Once S is a group, all the relations will surely be a congruence on S. So now question. We have seen that on a periodic finite semigroups and on a semigroup that satisfy mean L and mean R, the relations D and G are equal. Yes. Now, could there be another different class of semigroup that satisfy this equality? Meaning that not necessarily a finite semigroup does not necessarily satisfy this mean L mean R,
Wa alaikum
and
assalam.
at the same time
Ya kwana?
L,
Ba gajiya.
R, G, and all of them
Ji
are
an ce.
congruences.
Zo da flask.
Sorry, D and G are equal.
Will there be another
Ai,
class?
to da an sa
we
sai
need to
ki
investigate.
aje din.
Now, again, one could, as
Na gane,
matter
na samu
of fact, try to verify that for a semigroup S and for any A in S, the set SA, AS, and SAS
Are respectively left, right, and two-sided adders of S. You can
try to investigate that. And here the semigroup, you can allow one to be in the semigroup, let it be a monoid, so that A will be
Duk wannan shi
in
nan
the
guda
ideal.
12. Wala ba zan iya gano wanne shi ba.
So thank you for listening, and thank you all. It's now time for comments and questions.
Mun ta wanda zamu yi a gobe ne ba.
Yes.
Thank you, Dr. M. We are sincerely grateful for your time and for your patience
Yeah.
and for your legible way of keeping your lecture. You are so cool. Thank you, and God bless you.
Thank you very much.
At
you
this
very
point, our fellow colleagues and students on this platform would like to entertain questions. And once we affect our questions, we will not allow any other questions to come in. Let us affect it, and by the time we affect it, the presenter will respond to every question asked. May I first ask a question at slide 15?
Okay, slide 15.
Slide 15.
Okay, we can go ahead.
I realized that ux raised to the power of m minus 1. Where does that minus 1 come from?
Okay, this ux for n minus 1, you're referring to, right?
Yes.
Yeah. Look at this is ux for n in the previous line.
Okay.
Did you see it?
I'm holding my.
I'm pointing at
Yes,
it.
your pointer is, I have seen that.
Yeah, so you can split this and write it as ux
Okay.
M minus 1 multiplied by ux.
It's very true.
Okay, that's how it is.
It's very true.
The idea is just to have
XA here.
Okay.
You see that?
I've seen that.
Yeah. And then XA is C.
It's very clear.
Okay.
Thank you. That is all other members. Please identify by. May I first, Prof is asking questions. Professor Isa Garba. Is Prof there?
Thank you. Presentation. Yeah, it's quite interesting. Reasonable. I don't have any question.
Okay.
I just want very early. I was admitted to but never survived it at the number. So well done. It's okay. It's okay. Thank you very much.
Thank you. Uh, any who are those raising up their hands? Samad, Imam,
Yes.
Franco.
Thank you very much, the chairman.
Thank you
for
very
giving
much,
me
the chairman, for
Okay,
giving me
sir.
the opportunity.
Thank you, sir.
It's not a question, it's just not a question. It's just a comment. Dr. Zubair, you have done a good job. I really it's not easy to break down this. I so much like style. The issues he up are not even in the test. There are some things he clarified that were compactly stated in the book. I think we really appreciate, and the more so questions you raise at the end of the presentation. Since those questions, some of them are questions. Students should pay attention to those questions and try to look at issues. That last question, you talk about finding other classes of where the two P and J relations are equal, apart from
Yes.
the minimality conditions. I think that is a very serious question. I don't know whether it has been looked at in the literature, but I think the students should give it a look. We
Yeah.
really thank you very much for your presentation. You did a very wonderful job. Thank you very much for your
Thank you
presentation.
very much. Thank you very much.
Shaggy,
Yes,
Shaggy.
yes, sir. Good
So,
morning, Mr. Chairman, sir. Good morning, our able
Okay.
doctor, our presenter.
thank you.
And
Thank you, Madam
thank you
Mr.
very
Sagir.
much for this your wonderful presentation. Actually, sir, we have learned a lot because one thing with semi group, by the time, no matter how you read it, when somebody just give you a brief explanation, you will get it at times in a blink of an eye. You just see that you understood the concept. But sir, I have a little problem. Even though I have been coming across it whenever I read this trivia.
Okay.
There are so many times
Yes.
I'll be hearing maybe R is trivial, L is trivial, or they will say a canal of theta is trivial. All these trivialities I need more clarification on what is this triviality and yes, and then
Oh,
secondly,
okay. Go
uh,
ahead. Go ahead.
sir, the
Go
concept of
ahead.
this periodic semigroup and a final semigroup, what is their relationship? Are they the same,
Okay.
or they have or they have any difference? And I think
Okay.
that's all.
Okay.
And then sir, partial order. The issue of partial
Okay.
order, because you made mention of this quotient sets said to be partial order. So that partial orders, I need also clarification, and maybe the definition will help, sir.
Okay.
Thank you, sir.
Okay. Thank you for your questions. I think whenever I have explained during the presentation that once we say this L or this particular relation is trivial, it means the relation there is just equality. I have said it. It means that A and B are L related.
If and only if A equals to B. Whenever you have this scenario, then you can just say L, or the semigroup is L trivial. That is the relation there, L there, the characterization for the L is just equality. Two elements are L related, A and B are L related if A equals to B,
Or A and B are unrelated if A equals to B. So equality. So that's the meaning of triviality there. Did you get that?
Yes, 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 sir. Yes, sir.
Did you get that? Did you get
Yes,
that?
sir. Yes, sir. Understood, sir.
Yes, sir. Understood. Okay, good. Okay. Now, on the issue of partial, did you mention partial order?
Yes, sir. Yes, sir. In the place. Yes, sir.
Okay. So now let me go back to a little bit to the place. Look at this set, like S by L.
Yes, sir.
Yes, sir. So you see, this is just a quotient set with this less than equals on it. And how do we find this? Look at it in slide 2, that LA is less than LB because the element in S by L are actually quotient sets. They look like these equivalences. They are equivalences. Every element you pick in S by L it looks like this. LA1, for instance, LA2, LA3 contains many of them. So they are just the equivalence classes of L relation, the equivalence classes of L relation. So we define this order, this less than or equals on this set. So to pick an element here is to pick an LE. And to compare two elements in S by L is to compare LA and LB, like this. And how do we define this order? The order is defined in this way. That is, LA is less than LB if and only if S1A is a subset of S1B. Whenever this happens, then we say LA is below LB. And this is actually a partial order. And we know what is a partial order relation. A relation is said to be partial order or if it is reflexive, antisymmetric, and transitive. So you can go and check those basics. So actually, the way a manner this less than or equals is defined on S by L is a partial order relation on this. And that's basically what. So and what we are saying, this S by L is not a quotient. We have seen that. I'm sure Dr. Samad must have discussed in our early lectures that if L is a congruence, S by L is a semigroup, which we refer to as a quotient semigroup. But here, one need to be careful. This is not necessarily a semigroup. S by L is or S by R or S by J. No, it's not necessarily. It's just a quotient set, and we define this partial order on that. I hope that you must have gotten it correctly.
Yes, sir. Thank you, sir.
So is there any other question?
Yes, sir. The third one is issue of periodic semigroup. Because there.
Okay. Yes. You mentioned. I remember. Yeah, you are asking the question that what is the relationship between a periodic semigroup and a finite semigroup? You see, every finite semigroup is automatically periodic because that semigroup already has a finite number of elements, meaning that it terminates somewhere. So if you raise any element of the sets of the semigroup to some integer, certainly it is coming back, meaning that it will surely be an idempotent. So every finite semigroup is actually periodic. But it's not necessarily true that every periodic semigroup is finite. But once you have a finite semigroup, automatically it is periodic. These are the relationship. For example, I'm sure you must have discussed the monogenic semigroup, and there are other examples of bicyclic semigroups, which are finite and they are periodic. And there are others which are periodic, not necessarily finite, meaning that at certain power, some elements usually comes back and it keeps going on like that. Some terminate somewhere, some keep going on, some terminate somewhere, some keep going on. One of the examples I believe is in the first lecture given by Dr. A.T. Imam, where he used a particular elements of full transformation semigroup to generate a group where it terminates somewhere. And from there, you have a chain of a cycle, and you just pick those elements and get a group. So it is always true that every finite semigroup is periodic. Is that clear?
Yes, sir. It's clear, sir.
Okay.
Thank you
Okay.
very much, sir. I
Is
really,
any,
I really
do we have anybody
Chairman, sir, I'm raising up my hand.
Okay, you
Morning,
can.
sir. Morning, sir. Okay, thank you, sir. Yes, I want to also join others in appreciating the lecturer for all the efforts and the job well done. Yes, I want to first say that we shouldn't forget the video and the slide as we always do regularly. Then my point one is that please, whenever you are describing some of these things, some of the examples will be quite good for us to follow. For some of us who are not majorly doing works on semi-group as we have it, as you are describing. Then number two, like the case of the uh, ordering of the quotient, one would love to see if there's an example. One would love to see how the quotient operator, I mean, how you operate it with the order. For example, you are using an order that is maybe less than or equal to. Yeah, one would love
Yeah.
to see the way this I call it operators go. Then the last one I want to also talk about is this issue of idempotent.
Go ahead.
Idempotent, yes.
Yeah.
The
Yeah.
definition of idempotent here, uh, well, for some of us who are not algebraists, we use it in some ways in other areas of Lie group or Lie algebra as something that gives 0 when you raise to power n or something like that. Yeah. So, is there any relationship with the way it is defined there and here? Thank you very much.
Yeah. Okay. Yeah. The issue of idempotent here, I think if you raise something to power some integer and it gave you 0, we refer to that as a nilpotent, nilpotent element. If you raise it, and that is in the situation where you have 0 in the structure. Yeah. If you don't have 0, you cannot talk about nilpotent. So the important here, it has been defined in our previous lectures So the assumption here is any person following this lecture must have listened to all the previous lectures. And again, on the example, I will, it's not that it's a good thing. I think in my next talk, I will give some examples on how you can come up with this really quotient set. Just once you have a semi-group S, no matter how little the elements are, you can define the LR and then order them using the way a manner the relation L is defined, and you can have the order is trivial. But you make a point, but that those who are really not in the semi-group theory will always like to will be providing some of these simple examples in our next talk. Yeah, talk. Yeah.
Thank you.
Yeah. Okay.
Am I seeing any? Okay, you are free to go. Yes.
This is the secretary, sir. Just to add to the last comment on the idempotent, I think in analysis, because of the background of the questioner, I think in analysis, what we call idempotent in algebra is what they operators.
Okay.
Operators. Where is equal to them.
Yeah. Okay.
Okay. Thank you.
That's just what.
Yeah.
Thank you.
Okay. I think I can see a lot of people. There's Amina also raising of her hand. Amina Muhammad Lawal is there.
Amina, can you please answer your questions? Amina. Okay, who again? Who again? Can anyone come up with his questions?
Yes,
Alaikum.
Walaikum salam. Okay.
Okay, go ahead.
My name is Sakir Ibrahim
Okay.
from Ahmad Bello University, Zaria.
there's a lot of
Presenter could you justice the topic because there are so many aspects. We were talking class. Today we had beta explanation, but today we had nation. Thank you, sir.
Thank you very much.
Please.
Thank you, sir.
Okay.
Thank you, Mr. Iskir.
John Agba, I think I'm seeing John Agba's hands.
yes.
Okay, Ibrahim.
Yes.
Ibrahim, please pull down your hand. John Agba, go
Okay.
straight to the point.
Okay. It's okay, sir. I want to the lecture was presented in an expertise manner. And not a question directly. It's a answer to the the presenter addressed it in the context of what he was what he did today. But I think if I understand him, he was saying generally, because when he say anytime he hears something triviality in group theory in this, and I just want to add up a little. I don't know if Segri is with me.
Yes, sir. I'm with you, sir. I'm with
Okay.
you.
All right. The issue of triviality in mathematics is something that is, for instance, it's obvious. It's easy to see. It doesn't need any rigorous argument or presentation to see. For instance, when you say the identity element and the whole group, forms, they are subgroups of a group. They are easy to see. You don't need to, but it may be difficult to check other subgroups, for instance. So those two subgroups are trivial, for instance, as well as other objects and concepts in mathematics. So triviality means easy. You don't need to struggle mathematically to identify or to know. Then the presenter also addressed very well the issue of the difference between finite and periodic semigroup. But just to add up a little thing, like you say, every finite semigroup is necessarily periodic or torsion, you call it. And then the periodic itself is a semigroup that every element generates a sub-semigroup that is finite. I don't know if you follow me, Segri.
Yes, sir. I follow. That's exactly what I jotted. That every finite semigroup is periodic.
John
Pardon?
Agba, are you asking question or you are delivering another lecture?
No,
Just ask your questions. Ask your questions. When the argument of Segri came up, you have added your distance. Just if you have questions, ask. Because in the next few minutes we'll close the session for today.
okay,
If you
Mr. Chairman,
you said what?
Okay. Hello, I said no when I started. Okay, I said it was not a question. Add up to the question segregation act.
I said you will have joined.
I think what Mr. Chairman, what he's saying is on the right track. However, on the issue of triviality in general, what he says is true. The question that was asked was triviality on the L, R, the rest relations. Once we say L is trivial, it means here with size. That is, whenever you see a semigroup is L trivial, or is R trivial, It means the characterization of relations L are just equality, meaning that two elements are L related if they are equal, A and B, or A is related to B if and only if A equals to B. That is to be precise, because the question was precise. But triviality in general, sometimes you also need to be very careful about triviality, especially in many of our algebraic papers. Sometimes something that is called trivial might not necessarily be trivial. If you go a little bit, try to check it, you realize it's difficult. So triviality sometimes used to be very difficult in general. But in this particular instance, as questioned by Sagir, the question is precise. Precise about and other relations. So the triviality is equality. Anyway, you see triviality is equality.
Okay, thank you, sir. Can Agba bring down his hand, Mrs. Bakari from First of Ilorin?
Yeah.
Hello.
Hello, yes, Dr.
Mrs. Bakari.
Yes.
Okay.
Hello, Mr. Chairman.
Good morning.
First of all, I will
You have the floor.
start by congratulating the presentation was loudly and no interruption at all. And then I have a comment. My comment is, I think there is need to give illustrative examples in the presentation, but it is not. And then another thing that I have seen in the slide for the presentation, throughout the slides, if you look at the headings are written introduction. So I think there is need in each case maybe to have some slide with the introduction, preliminaries, and whatever. And then lastly, I want to ask a question that any necessary and sufficient condition for a semi-group to have an empty set of idempotents. Thank you very much.
Okay. Thank you very much, Dr. Amina. Actually, why we call this introduction, there will be other sequence of lectures. So this is just introductory part of Green's relations. That's why we allow it to just be introduction. In the subsequent ones, you will see, because it's a series of lectures. So this is just the introductory part. And the issue of idempotent, you may have a semi-group that has that the set of idempotent is empty. One trivial example one can give is a semi-group of natural numbers under addition. The set of natural numbers, 1, 2 continuously under addition. This set has no idempotent elements. Even though it's a semi-group generated by 1, but it has no idempotent. You can attach 0 to 8. If you attach 0 to 8, then it becomes a semi-group with only one idempotent as 0. In fact, there are many semi-groups without idempotent. So it's always possible. Thank you for your comments.
All right. Bye-bye.
Thank you. Yes.
Mrs. Dr. Udoaka. If Udoaka is not there, for University of Ilorin. Udoaka for University of Ilorin. I think on this note, I think we have to draw the conclusion to this lecture. This is exactly 11:30, and by our arrangement, we have agreed that when it's 11:30, we end our lecture for today. And not only that, we have reached the agreement that we will assess our questions, after which the presenter will respond to questions asked. The way we did it this morning, the class not taking, the question will continue going. The moment we have our questions, if about 5-6 people ask questions, the presenter will now respond to those questions. Before we draw the curtain of today's lecture, we would like the presenter to please address some minor corrections that you noticed while presenting the lecture before sharing it, so that the lecture will be in proper shape. I understand that the title introduction means that this is just today's lecture is all about introduction to race relations, and while the subsequent ones will be titled in line with what we have under chapter 2. The presenter, we thank you for today's lecture, and we wish you a very best in the forthcoming. After the corrected version of this thing,